Hi guys, welcome to today's video. We're going to be doing 2019 paper 1 question 7, and it's a pretty interesting question that links sequences and series and limits as well as coordinate geometry, so we're going to get into it. Okay, so here's our question. We're told the closed line segment from 0 to 1 is shown below, so that's just here. And we're given steps of the construction of the Cantor set. So step 1 removes the open middle third. So as you can see here, the middle third of the line here has been removed completely. That's now gone. Step 2 does the same thing to the remaining line segments. So these lengths in here, from here to here, on the left as well as over here on the right, are both removed. And this process of removing line segments from the remaining lines from the previous step is sort of repeated indefinitely. Indefinitely being a very important word in the question. We're told the set of points that are not removed during the process is the Cantor set. So the points that remain. So in this case we can see that both 0 and 1 should always remain, as well as 1/3 and 2/3. We have 1/9 here in step 2 and 3. So certain points are just going to keep their place in the set, and there's going to keep being more and more as we gradually go through the process. So now that we understand the question, part A asks us to complete the table below to show the length of the line segments removed at each step for the first 5 steps, and got to give our answers as fractions. So if we just go back up to our diagram, first of all, it's pretty obvious that the length removed in step 1 is just 1/3, so from 1/3 to 2/3. Step 2 removes 1/3 of 1/3 from both this side over here and also over here as well. So 1/3 of 1/3 is 1/9. So it does that twice, so it removes 2/9. Step 3 removes 1/3 of these line segments, which when you put 1/3 to the power of 3, because we're on the 3rd step now and that's a pattern, we're actually removing 27ths. So we move 1, 2, 3, 4 of those. So it's pretty clear what kind of pattern is forming here, because we're actually just squaring the length removed in the previous step to find our new fraction of the length removed. Basically the top line is being multiplied by 2 and the bottom line is being multiplied by 3. So if we do that again for step 4, we're going to get 8 over 81, or 2 to the power of 3 over 3 to the power of 4, and by multiplying that again by 2 over 3, we find that step 5 is 16 over 243. So that's A part 1. The main challenge is just to identify the pattern that's happening, but for doing that you're going to get 10 marks. So next we're asked to find the total length of all the line segments removed after a finite number n of steps in the process, and give our answer in terms of n. So as usual with these sequences and series type questions that come up in the end of paper 1, we're told to find an expression in terms of n for what will happen if this continues, let's say, indefinitely. So the total length of all the segments removed is going to be the sum of all the lengths removed during each step. So however much length is removed in step 1 and then 2 and then on to whatever n is going to be. So as you may have guessed, this makes this question sum to n, and this sequence is indeed geometric because there's a common ratio, which happens to be 2/3, which each step is multiplied by in order to find the next step. So we can just go to our log tables in order to find the formula for the sum to n of a geometric sequence or series, which we're going to be using. So now all that's left to do is first of all identify a, which is the first term of the sequence, and that's step 1, which is equal to 1/3, or is whatever we multiplied our first step by to find our second, and our second to find our third. So you can either divide step 2 by step 1, or really any step by its previous step, or you can just see that the top line gets multiplied by 2 and the bottom line by 3, which is pretty easy to see. So whatever way you want to do it, but you'll find that r is equal to 2 over 3, and n is just equal to n because we're told to write it in terms of n, so we want an n in our answer. Because we're asked to find the total length, we're just going to let what we're looking for be L, capital L. So having plugged all that in, our top and bottom lines actually simplify quite a lot, because we have 1/3 on the top and 1 minus 2/3 on the bottom. So that's obviously going to be equal to 1/3 over 1/3, which is just 1, which means that L is actually just equal to 1 minus 2/3 all to the power of n. And because we can't simplify this any further, we've actually found our answer. So for finding this, you're going to get 5 marks. So next we've got to find the total length removed from the initial line segment after an infinite number of steps in the process. So unfortunately we can't use what we've previously found in the above part of the question to do this, because we can't really do much with n when it involves infinity. Just not going to work. So we can either find the limit of this L, or we can use our formula in our log tables for the sum to infinity. But I actually think it's much easier just to use 1 minus 2/3 the power of n as n approaches infinity. So this is just going to be equal to 1, which stays the same, minus 2/3, which is less than 1. So we're going to be multiplying that by itself, and that is obviously going to approach 0. So we just get 1 minus 0, which is equal to 1. And in case you didn't know or didn't notice, when you have anything to the power of n, so let's say x to the power of n, if x is greater than 1, then the limit of x to the n is going to be tending to infinity, because this is just an exponential function, and as we know, exponential functions just go up forever. So that's one case. If x is equal to 1, then the limit of x to the n is equal to 1, because that's just 1 to the power of whatever, which is just 1. And if x is less than 1, so like in this case where we have 2/3, the limit is going to be equal to 0 of that specific thing, because it's just going to get smaller and smaller. So therefore 0 is our limit. And that's kind of useful to know if you're ever dealing with something involving limits, or in this case sequences in series. It just helps simplify things a bit. But no matter how you did A part 3, it's going to be worth 5 marks. B part 1 asks us to complete a table to identify the endpoints labelled in the diagram, and to give our answer as fractions. So going back up to our diagram, here are our points from A to F. So I think it's easy enough to see that A is going to be equal to 2/3, because our jump goes up from 1/3. After removing that part of the segment, we're going to land again on 2/3. B is going to be equal to whatever is 2/3 of the way between 0 and 1/3. So that's just equal to 2/9. C is going to be 1/3 of the way between 2/3 and 1, which is actually 7/9. If you just convert 2/3 into 6/9 and then add 1/9, and if you add another 9th, you will arrive at 8/9, which is D. E is a bit trickier to identify, so you need to be careful. We know we're dealing in 1/27 at this point, so we know that this point beside E is going to be the same as 2/9, except expressed in whatever over 27. And that point is just going to be 6/27, multiplying above and below by 3. So E is going to be 1/27 more than that, making E 7/27. And F is just going to be 2/27 less than 1, which is 25/27. And those are our points. Some thinking required, but there's no reason you couldn't get that out, I don't think. So all that's left to do is just put our values in on our table, which is also important to remember, and for that you're going to get 10 marks. So B part 2 asks us to give a reason why 1/3 minus 1/9 plus 1/27 minus 1/81 is a point in the Cantor set. So if we once again use our diagram to help, and we start at 1/3 here and take away 1/9, we arrive at B. If we then add 1/27, we arrive at E. And the next natural step to find another point in the Cantor set would of course be to take E and take away 1/81, as this is how we would split this length in here by 3 in order to remove the middle third. So in short, we know that this point that they've given us, that they've represented as this bunch of fractions added and taken away, is a point in the Cantor set because it is an endpoint of a segment, and that's a perfectly valid reason. There is more mathematical reasons, like, involving some more complicated reasoning, but this is perfectly enough to get you your marks. It's certainly what I would have put, because it's kind of just the intuitive thing to put. And for putting a reason like this, which is valid, you're going to get 5 marks. So finally, B part 3 tells us the limit of this series, which was referenced above, is a point in the Cantor set, and we're asked to find this point. So once again, we're dealing with a geometric series where A is equal to 1/3, the first term, or is equal to minus 1/3, because we go from 1/3 to minus 1/9, and once again back to 1/27. And because we're dealing with a limit, we are of course going to be using our sum to infinity, which is just here in the log tables, is equal to A over 1 minus R. So given our sum to infinity formula, our limit is going to be equal to 1/3 over 1 minus 1/3, or 1/3 over 4/3, which just simplifies to 1/4. And that's our limit. So nothing too difficult there, and that's worth 10 marks. And that's actually it for this question. I hope you enjoyed the video. If you did, there's going to be other similar videos in the description, which could help you brush up on your sequence in the series, as well as some other helpful resources if you find you're struggling. So thanks for watching, and I'll see you next time.